Hey everyone, so welcome to a little final exam review. So a couple of things. Your final will be about 15 questions, no more than that, maybe less, covering chapter 4, 5, and 6. And so a couple of things you need for that final. You need your calculator, right? Scientific calculator that does the integral. Otherwise, you may have to use Desmos to evaluate integrals, but that's all you should use Desmos for. You want to have your formula sheet where all you have the formulas for calculating all the applications that we did in chapter 5. And you want to have your integral tables, your tables of integrals, because I will ask you to do at least a couple of problems where you use integral formulas that are given so that you can find more complicated integrals. So those things you need to have in front of you, at least beside you for your exam. And of course, your notes you may use. And then your brain. So this review is about 10, 11 problems. And again, I'm not telling you what's on the final. I'm just giving you some practice problems. The best way to prepare for the final is to have done the homework, to have watched the videos, and then I think you'll be pretty comfortable with it. Okay. So again, I'm going to work through them kind of fast. So if you have the problems in front of you, then, pause the video, do them, and then just check your work with mine, I think is the best way to kind of go about it. All right. Okay, here we go. Okay, so we're going to start with chapter 4, which was the introduction to antiderivatives and working backwards from derivatives back to the original function. So this particular problem, the integral of 1 over x to the 4th, is asking you to find the function that has a derivative of 1 over x to the 4th. So just like derivatives, we need to rewrite this. I'm going to bring the x up. So I'm going to write it as x to the negative 4 dx. And I'm going to apply my antiderivative rules, which are that you add 1 to the exponent and then divide by that. Okay, now at this point, you don't need to write this step, right? I wouldn't normally write this step. I would just add 1 to the exponent. So I'd say, okay, negative 4 plus 1, that's going to give me x to the negative 3, and then divided by negative 3. So it's going to look like this, plus c. The integral sign drops once you apply the antiderivative rules, and then you're going to write your answer in a way so that we don't have negative exponents. So I'm going to flip this guy back to the bottom part. So I'm going to have an answer of 1 over negative 3x cubed plus a constant. And that is my antiderivative. So anytime you're doing an integral, an indefinite integral, you're going to have a plus c on it. Okay, let's take the next one here. So again, we're looking for antiderivatives. So I'm going to apply my rules. So to get the antiderivative of e to a power, it's always going to be e to that power, but divided by that. So the rule I'm using is we have the rule, if you have e to the kx, that the antiderivative is e to the kx divided by the k. Okay, so I'm using that rule. So it's e to the 3m divided by the 3. Oh, and I need to rewrite this guy here before I can do my antiderivative. Let's think of this guy as m to the 5/3. And that way, when I add 1 to the exponent, so now I'm just using the power rule like I did earlier, add 1 to 5/3, that's going to make it m to the 8/3, and then divided by 8/3 plus the constant. Now, I'm not going to leave this improper, well, shall we say complex fraction. So I want to get rid of that 8/3 in the denominator so I can flip it. I can multiply by the reciprocal. So let's write this e to the 3m over 3 plus, let's flip this, let's make it 3/8. And then that m to the 8/3, let's put it back in a radical form. So that'll be back as a cube root of m to the 8th plus a constant. And again, you can write these answers in slightly different ways. For example, that, radical can be totally on the top of the fraction, the whole thing, over 8 if you like. Okay, so anything equivalent. All right, so antiderivatives. Now, kind of an application of this would be, I could give you a derivative in an application. So say give you a marginal cost function and ask you to work it backwards and find the cost function. So if you are given the derivative of the cost, the way to get the cost function would be to undo it. So you'd want to take the antiderivative of negative 0.02x plus 29. So if you do the antiderivative of that, that would get you back to the cost function. Okay, so first let's start with an antiderivative of this, which would get me, let's see, if I use my power rule, negative 0.02x, raise it up to the second power, divide by that second power, and 29, because it's a constant, we just give it the x, and then don't forget plus c. Anytime you're doing an indefinite integral, you have the constant. All right, so this is my cost function. Let me do a little reducing of this 2 here and this 2 here. So I can make this into a negative 0.01x squared plus 29x plus the constant. Now they gave me some information in the problem so that I could actually find the value of the constant. They said up here in the problem that the cost is $10,025 when the production level is 200. And they said X was the production level. So, okay, I'm going to plug in X is 200 and set the cost equal to the 10,025. So plugging in the information they gave me, that will allow me to find the constant. So they said, oh, why am I putting in 10? They said 200. I don't know why I'm stuck on 10 here. So they said production level 200. So 200 goes in here for both of these X's. And it's going to equal a cost of 10,025. So let's solve for the constant. So I'm going to type all this in my calculator, and then I'll solve for C. Okay, so typing all this in, it looks like I got the 5,400, and then I'm going to move that to the other side. And so I find out that my constant is equal to, it looks like 4625 if I did that right. Whoops, 4625. So remember, your answer is the cost function. It says find the cost function. So be sure it's clear what your answer is. So the cost function C of X is going to be this negative 0.01x squared plus 29x plus the constant of 4625. Yeah, gosh, writing is bad here. 4625. And so you're going to box that or circle it or make it really clear that that's your final answer there. Okay. All right. So that's how we can use antiderivatives to work backwards from a derivative to the original function. Okay. Again, all in chapter 4. The last thing in chapter 4 was we figured out how to evaluate definite integrals. Now I know definite integrals can be put in your calculator to evaluate, but I will ask you on the final to do a couple by hand. The rest you'll do with your calculator, but I want to see that you can do and evaluate some by hand. So let's try number 4 here. This is a pretty straightforward one. So evaluating by hand requires you first to get the antiderivative. So that's going to be 2x, raise it up to the 4th, divide by 4. Minus 5x, raise that up to 3, divided by 3. We do not put a plus c on these integrals because we'll be evaluating, plugging in some numbers. Let me do a little reducing before I plug in. Okay, so I want to reduce. If I'm doing things by hand, you always want to reduce, save yourself a little bit of work. All right, so here's what I get when I reduce. So then once we've got the antiderivative, we're going to plug in the upper limit. So we're going to plug in 1. So we're going to find the function or antiderivative value at 1, subtract the antiderivative value at 0. The good thing is here plugging in 0 is probably going to be 0, right? So I plug in 1, 1 to the 4th divided by 2, minus 5 times 1 to the 3rd divided by 3, minus, and then you plug 0 in. Okay, 0 to the 4, that's going to be 0 and a bunch of the 0 there. So forgive my shorting it up a little bit. But so that's going to give you 1 to the 4th, which is 1/2 minus 5/3. And of course, minus 0. So if we just do a 1/2 minus 5/3, I'm going to use my trusty calculator. There's no need to make a mistake doing fractions by hand. I get -7/6. And so the value of this definite integral should be -7/6. And there's my work to show that I'm doing it by hand. That's what I'm looking for on your paper. Okay. Okay, let's do another one by hand. So this one's a little messier. We're going to do an integral from 1 to the letter e of -6/y dy. So it's possible, because we have an e there, that our answer might have e's in it. Okay, let's get our antiderivative. So I'm noticing on this one, when we have this -6/y, if that was y to any power, I would bring it up. But when it's just a single y, remember, we have that rule. If you have an integral of 1/x, okay, that's going to be a natural log. And in this case, we have a 1/y. So it's just going to be a natural log of y. So the -6 is just going to hang out there. I'll write it like this just so you can see. So it's as if you have a -6 and then a 1/y dy. So the antiderivative be -6 natural log of y. And that will have to be evaluated from 1 to the letter e. Well, I say letter, the number e. Okay, so let's plug in. E plugs in first, so it's -6 times the natural log of e. I can drop absolute value because e is a positive number. Minus -6 times the natural log of 1. Drop the absolute value. 1 is a positive number. Okay, so let's see. The natural log of e. Well, the natural log and e are inverses. So that just becomes 1 times -6 minus -6. And the natural log of 1, any log of 1, is 0. So we get -6 minus 0, -6. Is our value of that integral. And there's my work to get it. Okay. All right. Again, I'm going fast, but you want to pause the video and make sure you're kind of working these along with me, or working them ahead of time and then just checking them with my work. So that's a quick run through of chapter 4. That was the gist of it anyhow. There was also in chapter 4 evaluating integrals using tables. I will ask you that. I will not ask you to evaluate integrals by substitution. Okay, I've mentioned that a couple times, but do you know how to use tables? All right, let's jump into chapter 5, which was all the applications of integration, where that formula sheet will be very handy. So this first application is for the Gini index. Now there's a lot of applications, so you have to kind of know what formula goes with what. Gini index is pretty straightforward. So we're coming up with a measure of income equality here. So the Gini index formula is, to find a Gini index, you're going to take the integral from 0 to 1, and you're going to take x minus your Lorenz curve, dx. And so again, for these problems, if it doesn't say evaluate by hand, you're going to use your calculator. You're going to set up your integral. So I'm going to do the integral from 0 to 1 of x minus my Lorenz curve, which is x to the 2.1 dx. Now remember, Gini index is as a percentage. So I'm going to put this in my calculator. I'm going to type in my integral from 0 up to 1. And I'm going to put in x minus x to the power of 2.1. And I'm going to get an answer, and it's going to be, a decimal. But then I'm going to change that decimal to a percent. Sorry about that. My calculator is just on the fritz lately. So I think I have this value somewhere I can get for you. Hang on, let's see. Okay, so you get a decimal and then your Gini index is as a percent. So my Gini index is going to be 35.4838. So that's a measure of income equality. Now, the closer to zero, the smaller your number is, the closer to equality you are, right? Because remember, the measure of the area, the bigger the area, the bigger the inequity is. Okay, so again, that's just plugging in a formula and then giving the answer. Okay, number 7, areas are kind of a big application because matter of fact, all the applications really do involve area if you think of it. Find the area bounded by these two functions. All right, so I don't need to necessarily have a perfect graph. And if this is the final, I'll probably give you the graph of this. But I can tell you that you've got this one quadratic with a negative. So I know it would be some kind of a parabola facing down. And then the other with a positive x squared would be some kind of a, parabola facing up like this is the image that I kind of have. So what I need to do if I'm looking for the area is first find the intersection points. Where do they intersect at? And then I can know where to put the limits of integration on my integral. So let's do that. So we find those by setting these equal to each other. So negative x squared minus 2x plus 18, we set that equal to x squared minus 2x plus 16. So to solve this, I'm going to bring all these terms on this side over to the other side. I'm going to get it equal to 0. So I get it equal to 0. So if I add x squared, I'm going to get 2x squared. If I add 2x, oh, that's going to cancel that 2x. Okay, that's fine. And then if I move my 18 over, it looks like minus 2. Okay, I can factor that. One thing I could do is factor out a 2. That'll give me x squared minus 1. You could also do this by a square root property. I'm just going to continue with my factoring. That's a difference of squares, so it's going to factor to x plus 1x minus 1. And so setting those equal to 0, I get that x would be negative 1 and x would equal positive 1. Okay, so my points of intersection are going to be at negative 1 and positive 1. So if you kind of visualize this graph here, it's going to hit here at x is negative 1 and over here at x is positive 1. So to find the area, I'm going to be integrating from negative 1 to positive 1. Now the upper curve, right, if you think about this area we're finding, which is the area between these curves here, the top curve or the upper curve is the parabola that faces down. And then the lower curve, being the one at the bottom of the area, is the parabola that faces up. So the integral, because I always set it up upper curve minus lower curve, will look like this. The upper one being the negative x squared minus 2x plus 18 minus the lower curve, which is the x squared minus 2x plus 16 dx. You could type that all in your calculator right now and get your answer. Or you could clean it up a little bit. I kind of like to clean that up a little bit, and then I can write a nicer looking integral here. So let's see if I could just make that a little better. Let's combine my like terms here. So let's say I clean that up. It'll be easier to put in my calculator if I do that. So if I combine the x squareds, I'm going to have a negative 2x squared. And then again, the 2x's cancel. And then 18 minus 16 will give me plus 2 dx. Okay, so if I input this in my calculator, that's going to give me my area. So take a minute, do that. Okay, so you should get a value of 8/3. Now, if your calculator gives you, some decimal that's going on forever, convert it to a fraction. Use the button on your calculator that converts decimals to fractions so that you don't round it off, right? I always want you to give me exact values, okay? Don't say it's 2.333. That's not good, okay? To keep it exact, convert it back to its fraction form. So this is my area, and since it is an area, I'll say square units here, okay? But again, I'm not going to evaluate by hand. I'm going to use my calculator to do it. You won't have time to finish the test if you do all these by hand. Okay, so that was a big application of integration, is finding these areas. And so here's another example of using areas, is if we find a consumer surplus or producer surplus. I just chose one of them. So here we give you a demand for a certain item is given by this D of X. Find the consumer surplus if the equilibrium price is $10. Okay, so remember our equilibrium point is always some X value at equilibrium and then some price at equilibrium, right? An X and a Y. And so they're giving me the Y value. They're telling me that this price at equilibrium is 10, and I'm going to have to find the X value or the quantity at equilibrium. Because in order to get consumer surplus, right, the formula that I like to use is I use the formula where we integrate from 0 to the X at equilibrium. And then we do the demand function, D of X, minus the price. Okay, so this is the formula that I use. If you're welcome to use that other formula, to me, this is just a little bit cleaner. So it's how I've been demonstrating in the video as well. Okay, so I have most everything. I have the demand function. Okay, I'm good on that, right? I've got this guy. I've got the price at equilibrium, but what I need to find is this X value at equilibrium. I need the quantity at equilibrium. Okay, so what I'm going to do is use that demand function and plug in there. So I know that D of X equals 200 over X plus 4. And so I'm trying to find X. I know the price is 10. So I know that D of X is 10 equals 200 over X plus 4. So I have a little solving to do here. So let's solve for X. Let's multiply both sides by the LCD of X plus 4, and that'll cancel out the X plus 4's here. That'll give me 200 equals, let's distribute 10X plus 40. Let's solve for X, right? Move your 40 over, and that'll give me a 10X equals a 160, and divide by 10, 16. Okay, so the quantity at equilibrium is 16. So this is 16 here, right? So now I can set it up. A consumer surplus is going to be the integral from 0 to 16 of 200 over X plus 4 minus 10 dx. Type it in your calculator and you'll get your consumer surplus. Now remember, consumer surplus will be a dollar amount. So when you get that answer, you're going to label it money, okay? So that's your dollar amount. Let me see if I have an answer for that for you. Because my calculator, like I said, is kind of on the fritzy. Okay, here we go. So that should come out to be $161.89, right? Okay, so again, I said it is area because really what you're doing, if you kind of imagine the picture here, right? We've got units across the bottom. We've got a price on this axis. And so what you have is you have this demand function. And again, I'm making it up. I don't know for sure, but you've got some demand function coming down probably like this. And then you're getting the area between that and the equilibrium point or price here. Now that was a bad line here. Let's try that again. So you've got some equilibrium point right here, right, where the quantity is 16 and the price is 10. And you're getting, for this consumer surplus, you're getting this area between here. That's why I do upper curve demand minus lower curve price. And that's what gives me right there my consumer surplus. Okay. All right. So there's another application from chapter 5. There's bunches of them. Again, I've just chosen a couple examples to give you for this review. Okay, chapter 6. This is where we have our functions of several variables. The good thing about chapter 6 is you get to review all your derivative rules. Because I haven't done those in a while, it's kind of good to bring those back. You need the product rule, quotient rule, chain rule, all of those come into play when we do our derivatives of these multivariable functions. Okay, so this first one is just a basic find the derivatives. So I'll definitely ask you about that. Your derivative with respect to x means you focus on x as your variable and treat y as your constant. So the derivative with respect to here would be 4x cubed, right? The derivative of x to the fourth is 4x cubed. And then the second term there has an x in it, right? So I'm looking at this term here. And so the derivative of that, bring the 2 down, is going to make a 12. So that's going to be 12x to the first, and then the y cubed just comes along for the ride there. Okay, so that's our derivative with respect to the x. Now let's do the derivative with respect to y. So now you focus on y as your variable. So any term with a y is going to have a derivative, and you treat x like a constant. So when I'm doing the derivative with respect to y, this guy here, this x to the fourth, goes away. And then the derivative of the next term, let's see, 3 times 6 would be 18. Keep the x squared there, and then y drops to the second power. And then that last term, power rule, 4 times 4, 16. Y drops to the third power. Because remember, derivatives, you bring the exponent to the front and multiply, and then you lower the power by 1. It's hard going back to derivatives when we've been doing antiderivatives for a while. Okay, so you just got to focus on keeping those things organized. Okay, number 10 is find the critical points. Now, critical points of multivariable functions are just like critical points of our previous functions. They are where the derivative equals 0. So in order to find critical points, I have to find both of the derivatives, and then I'll be setting them equal to 0 and solving. Okay, so let's get our derivatives with respect to x and y. So with respect to x, I would bring the 2 down. So this would become 2x over 2. I'll reduce that, plus 5. And then the derivative of negative 3xy is negative 3y. Derivative with respect to y is 2y over 2. Cancel those, plus 1 minus 3x. Okay, so again, these are going to knock out these 2's here. So setting them equal to 0, so I end up with x. I'm going to reorganize minus 3y plus 5 equals 0. And the new equation here, y, oh, well, let's switch that around and put the x first. Sorry. Let's make it negative 3x plus y plus 1 equals 0. So you set these equal to 0, and then you have to solve this system. You can solve it by substitution. You can solve it by elimination. Pick one of those methods to solve because you're looking for an ordered pair. I was thinking I might try a substitution method because I'm noticing, this x in this first equation is almost by itself. So here's what I'm going to do. I'm going to take and solve for x. I'm going to keep x on this side, and I'm going to throw on the other side, move over 3y, and subtract over the 5. So I just took this equation and I did a little solve for x. And now I'm going to do a little substitution, and I'm going to substitute 3y minus 5 in for the x in the other equation. So I've decided to use substitution here. All right. So substitution is going to give me negative 3, plug in x, which is 3y minus 5. Plus y plus 1 equals 0. You can now solve that for y, and then we will have a y value, and I could plug back in and get x value. Okay, so take a minute, solve this for y. Negative 9y, let's see, plus 15 plus y plus 1 is 0. Combining like terms, negative 8y. Let's throw that 16 to the other side. And so again, I'm going fast, but pause your video so that you can practice this. So as far as a critical point, I've got my y value, right? So there's x, a y, and a z, depending on what they ask for. So I got the y value of 2. Let's plug that y value back up into here and get the x value. So x will be 3 times 2 minus 5. So that gives us our x value of 6 minus 5, which is 1. So my critical point, 1, 2. Now, if they ask you for the x, y, and z, then you would just plug this x and y back in the original and get the z value. It just depends on how they ask the question. If they just say the critical point, I'm just going to give the ordered pair. Okay. All right. That's how you find a critical point. Now, the next part is determine any maxes and mins. So we get to practice all of what we've just done. We've got to find a critical point, and then we run the D test. Okay. So take a minute for number 11. Let's get the critical point, and then I'll run through the D test with you to remind you. Okay, so if you get your derivative with respect to x and y, set those equal to 0, and then you should end up with a critical point right here of 2, 2. Okay, now we're going to figure out, is that critical point a max, a min, or maybe a saddle point, or maybe we can't figure it out. So the only way to do that is that D test. Okay, so again, I'll probably give you an application form of the problem, but it's all the same work. It's just that maybe 2, 2 represents a number of, I don't know, nails and hammers or something. So let's get the D test. So for that, we need our second derivatives. So each of our second derivatives, and then we will run them through a little formula. Okay, so take a minute, get your second derivatives here. So my second derivative with respect to x, if I do that again, 6. Second derivative with respect to y is a 4. And a derivative of x first and then y. So when I do this mixed derivative, I use this first derivative of x up here and then take the derivative of y. And since there is no y there, that's going to be 0. So then I run through the formula that says to get the value of D, you take your x, multiply by your y, and subtract from that your mixed derivative squared. So for us, the value of z is going to be 6 times 4 minus 0 squared, and 6 times 4 is 24. So D comes out to be a positive value. All right, so since D is a positive, what I do is I look back at the xx derivative. That's what's going to tell me. And since this xx derivative is positive, okay, so I'm going to say, and z of xx is also positive. Think about when your second derivative is positive. That's meaning the concave up, the happy face. And so if that's a happy face, that means we have a minimum. Okay, so let's figure this out. So we want to get the ordered triple. So we have a relative minimum at 2, 2, something. So I got to find this z value. I've got x and y. I need to get z. So we're going to plug 2 and 2 back into that original to get the z value. So do that. So it looks like our minimum value should be negative 17. So relative minimum at 2, 2, negative 17. Or you can say the relative minimum is negative 17. It occurs at 2, 2, right? That's a different way of saying it. So that would be all, our work for finding any extrema. Again, really important that you show the D test. You don't ever assume a critical point is something without the proof of it. All right, well, that's been my super fast final exam review for you. I hope it's been helpful. Again, I hope it's narrowed down a little bit, but remember, I can't give you an example of everything. You have to have done the homework and do the practice. And if you, review the notes from the videos, I think that really helps as well. Okay, good luck, gang. And hopefully it'll turn out the way that you want it to.